All right, we'll go for now then. Okay, folks. Happy Tuesday, as no one says. All right. How are we doing? Maybe, okay. I don't want to prejudge your Tuesdays, so imagine it's a fantastic Tuesday. Okay. All right, a few updates on the course. So the most critical update, actually, is that homework 1 is now posted. Okay. Glad that makes one of us. All right. All right, it's up. So basically, the way we're doing this is a coding assignment as promised, all right? And the way that you'll be submitting it, and this is, I will say it's a little bit of an experiment. We never tried doing a full class submission of code this way before. So they might have some updates as people have questions. But make sure you have a Google Colab account, a Google account that's doing Colab, and you will give us a link as your homework submission that you will submit via Canvas that we can click on and run your code, and when we run your code, it should work. That easy, right? Okay, just like we've been doing in our coding lectures, all right? It is doing gradient, for undergrads, it is doing gradient descent on higher order polynomial models to fit some data. And you're going to show me how well it generalizes when you add more power to the model. Okay, so it's going to generalize, you're going to be challenged to generalize what you've learned about gradient descent in order to optimize these models. All right. Basically, how good are you at gradient descent? You're going to be excellent, which is great because that's a lot of what we do in modern machine learning. If you're a grad student, we also know that these are linear models. We all know this, and that there's a nicer, easier way to not use gradient descent for linear models using our linear algebra formulation we covered a week ago. All right. So grad students, you will, in addition to the gradient descent approach, you'll do the same assignment, but then you will just substitute what was done for the previous problem and do it with the linear algebra approach, where you solve directly for the optimal model parameters. Okay, that's what we'll do, and it is due next Friday at 5 p.m. So, what, 10 days from now? Okay, I recommend starting early. All right. And one thing that we will add, and one thing I highly recommend, and this will be an ongoingly updated document, is our homework FAQ page, frequently asked questions. All right. Believe it or not, many students have similar questions. And so what we do is when we find such things, we put them on a Canvas page. There should be a link on the very front page of Canvas you click on. So check there first before you panic email in the middle of the night. Just save yourself some time, okay? And see if anyone has it, all right? Now, we will be updating this document, including an important set of instructions that we have not covered yet in class, which is how to import data from a file into your workspace as a variable in Python, as a NumPy array, okay? Because along with the homework assignment up on Canvas is a data file. That's the data you're going to be fitting, okay? Be 100 data points, and I'm going to want you to fit the data based on 20 data points, and then test how well it generalizes against the other 80, right? That's what we'll be doing. Okay? I imagine there'll be more questions as things go on, but any questions to start with? I can't imagine there'll be too many, considering we just dropped this. Okay. Question? Those blocks that you I would recommend, and this is hard to standardize, so this is a great question. The question is, what kind of commenting format is there, okay? I would recommend trying to follow a similar format we did from class where you create new code blocks and to comment it to be readable. Why? Now, we have not set an official, we need to set an official rubric as to, it's hard to say like an official rubric for grading code when if it works right, good job. Okay? If it don't work right and we can't read your code, it's extremely hard to give partial credit. Okay? Right? So right now the current instruction is to try to be neat with your code, follow the general format we did from class, okay? Explain what you're doing. But if things are getting out of hand, we'll start, we stay tuned for maybe more instructions, okay? In case, because again, we have never done a thing like this of this size where we inspect the code live on a link like this. So be a bit of an experiment, but please be reasonable. And if you need a guide, just follow how we do it in class mostly. Great question. Any other questions? We're all excited to code for ourselves. Okay, yes, great, awesome. So, where were we? So we've had some fun in the last, well, all semester, let's be honest, of course, okay? So today is the 3rd of February. The groundhog saw a shadow. I'm sorry. We're not loving I'm not loving the winter down here, I'll tell you, okay? Man, and I was telling the morning class, my hands have been cracking like crazy. It is so dry. So I'm not normally a moisturization guy, but I am today. So, all right. So we've got, so 3rd of February, we are going to continue on backpropagation, okay? This is such a central element for how modern machine learning functions in practice. Let me change my view here. All right, here. Yep, backpropagation. All right, because what does backpropagation give us? What is it trying to give us at the end of the day? When we run this backpropagation that we talked a little bit about a week ago, what's the result of it? Anyone? Anyone? What's it trying to get us? Does it rhyme with Schmadiant? Yes, it does. It rhymes with its gradients, right? So much of our approaches we're going to take are going to be based on gradient descent. How do we get that gradient from a really complicated model, right? So recall, backpropagation continued. So recall, we introduced a neural network which is a model composed of a computational graph. Okay? And by graph, for those who are new to this kind of math, it's basically think circles with arrows pointing in other circles, right? So, and particularly we had this type of neural network. This is an example where we have all of these connections going forward. Whereas a feed-forward neural network, it goes in one direction. There are arrows that are implied with all of these that move forward. Okay? Or these are your inputs. This is your output. And what's going to come out of that neural network is an output, and we want that output to be good. What is good? Well, it's defined by that cost function, okay? If it's a supervised learning method, that cost function is going to probably be predicting labeled data, right? That's what supervised means, okay? If it's a reinforcement learning method, that cost function could be the reward. What is good? You know, we define what, you know, if we are sending recommendations, if we're Amazon and we're sending recommendations to the person clicking around on Amazon to buy more things, did they click on it? Yes or no? If yes, oh, that's good. Reward. If not, that's bad. Okay. So that output will then be shoved through what we call a cost function, or what is also frequently called a loss function. What is the difference between a cost function and a loss function? Absolutely nothing. Okay? You will see both things written in the Goodfellow textbook. at all. Particularly on the chapter on backpropagation in chapter 6, they'll call it a loss function. Okay? Where it might be listed as L of your decision vector W. Okay? But in the supervisory context, meaning that we are trying to compare a labeled output with another labeled output, we compare our prediction, y hat, with our actual data, y. What's an example of a loss or cost function that we've used in the past for supervised learning? Mean squared error. He doesn't even go here. Don't let him show you up. Mean squared error. Example is the mean squared error. Or MSE, which you'll be using for your homework. Okay? All right? And it'll be one of the first ways we will train a neural network ourselves. All right? But there could be all kinds of loss and cost functions, right? So you will have a neural network, and this one has multiple layers. Okay? So we call it a multi-layered perceptron, or MLP. Okay? One of the quintessential neural networks. And guess what? Who's heard of deep learning in their lives? Deep fakes, deep learning, deep things. Guess what? It's deep. We're doing deep learning now. How'd we get here? Oh my goodness, I don't know. Like and subscribe. Right? So the more of these layers that you add, which who gets to decide how many layers there are? We do, right? The deeper the network is. All right? Now, one thing you'll find, just as a practical note, so again, what are we trying to add when we're doing the learning? What are we actually learning? What are we actually optimizing? What are our decision variables for this neural network? The weights. And that's correct, the weights. We would also say the biases. There are ways to do it with, as we covered last time, there's ways to treat them all as weights, but generally speaking, weights and biases, right? So in order to get these weights and biases right, the deeper your network, you're going to have so many more weights and biases, right? Guess what that means? You need also a lot of data. So in order to train these big, deep networks, we need big data. All right? That is part of one of the things that is now powering this whole machine learning revolution, is that people realize, oh, we need really big networks. Oh, we need a lot of data. We have to be able to train these networks, right? Okay. So anyway, so we have this multi-layer perceptron right there. But in order to train it and get those weights and biases, we need an algorithm, an optimization algorithm. So recall, for ML, we need data, a model. The model is our MLP, right? We need some cost, or now maybe a loss function. And we needed the optimization algorithm, right? Okay. Anyone want to guess what optimization algorithm we'll be using? That gives us the derivative. What do we do with that derivative? Gradient descent. We will use gradient descent. Okay? That is true. We will be using gradient descent. We've done it a bunch of times. Question? You can use gradient descent. Well, sorry. I thought you were going to go the other way. Can you use something other than gradient descent to find the weights for a neural network? Absolutely, you can. Another one that I don't know how, it definitely was a prominent technique for a while were genetic algorithms. Anyone know the video game called StarCraft or StarCraft 2? Has anyone heard of this? Anyone heard of a game before? We're live? We're okay, good. Okay. All right. So yes, it is such a common trope in the machine learning world that a benchmark is, can you get a computer to play a game better than a person? Classic examples are back in in the days of chess, Deep Blue and things like that, going up against Garry Kasparov, the chess player. And decades ago, computers outplay humans easily. Now, algorithms like Stockfish just crush people. People cannot beat them in chess. But chess is a very well-defined game. There's not a lot of uncertainty. You see a lot of pieces you see all the pieces on the board. You could literally think many, many steps ahead. The combinations become crazy, but there are smart ways to do it that don't necessarily involve deep learning, by the way. There are all kinds of algorithms for it. But another thing is video games, because for some reason people are nerds. And so there was a challenge. It's actually a scientific publication on an algorithm called AlphaStar that would play StarCraft, which is a real-time strategy game where you're moving soldiers and aliens to shoot each other. Very violent, etc. But they managed to make an algorithm that was a giant neural network that would do reinforcement learning to play against itself to become better at playing the game of StarCraft. And the algorithm that they used was more or less a genetic algorithm where you randomly change the weights and you say that one did better than that one. This one is now apparent to many children neural networks that are similar but slightly different. And this one is bad, kill it. Very brutal, right? And they continue until they came up with a better algorithm. That's a genetic algorithm approach. So it's not only gradient descent. All right. All right. So we're going to be doing gradient descent, but not entirely, right? So the gradient descent, theoretically, would mean for something like trying to fit data, where you have some input and some output and a bunch of data, right? You have a bunch of data points, many data points, right? And you would assess the gradient of a particular model with some parameters. It's some function of our parameters W, okay, by checking how it fits all those data points. And we did this in a loop when we were doing gradient descent. We would add, every time we'd add a data point, we'd add the gradient to it, right? For every data point. But you don't have to do that, okay? You could randomly select maybe one data point and get the gradient from that and apply it. You could do that, right? That random selection of that data point now adds some randomness to our gradient descent algorithm. But it's actually pretty darn good at training models, even though the amount of data you might have is big. We can train it off comparatively smaller data, okay? So when you can randomly, you can randomly select data points to evaluate the gradient. And overall, this is called stochastic, meaning random gradient descent. Stochastic applies to random processes, right? One time when I was in graduate school, I took a small vacation, but I didn't tell my grad students where. I still showed up for the remote lab meetings. And I went to Vegas. So I said I went to a stochastic systems conference because there's randomness in Vegas. So anyway, they didn't buy it. So Now, you could choose to compute the, if you choose just a single data point for which you would get a gradient, a stochastic gradient descent. But normally we don't just choose one, we choose a batch of them, okay? Some small batch. And then average, say, is it common to randomly select a batch of points to compute the gradient from. Hey, Jacob. All right. Thank you. I'm looking for my grad student for validation. Gave me a lecture on this the other day, what technically stochastic gradient descent was. Anyway, so anyway, so you don't have to do it for every data point, right? So I just want to introduce that concept. But you can see how that's not hard. You just have to randomly select some data, okay? And there are random number generators within code. That's not hard, right? Okay, but we still have to get that gradient. And backpropagation is a computationally efficient method of computing a gradient for computational graphs. The key sticking point is that old little bugger, the chain rule from calculus. I see some smiles, good. People remember the chain rule and its perniciousness, okay? Because as we covered last time, if you have some kind of input x into y into z into e, all right? And let's just assume there's a function that maps with these arrows from one to the other to the other to the other. And if you want to know the partial derivative, so in this case where p is going to be equal to 3 functions of x, right? Function of a function of a function of x. And you wanted to take a derivative, partial p, partial x. You have to do the chain rule a couple of times. You would first take the derivative of this outermost function, call it f prime, and f of x are still on the inside preserved, but then we have to take the derivative of the inside, which will be f prime of f of x. Derivative of this, which then is like a nesting doll, gesundheit. Derivative of the inside, f of x, right? That gets nasty if you do it symbolically, but we have a clever way of getting these particular values, recalling that f of x is y, and f of x is z. All right, look, f of x is z, and f of x is y. So this became f prime of z times f prime of y times f prime of, of x. Looks much simpler, given the fact that if we are going to use this neural network, we will first have to evaluate it or inference it, meaning we will just actually evaluate these functions and see what comes out. So at some point in the code, we will have to compute f of x, which is equal to y. Already, store that value. We'll have to compute f of y, which is equal to z. Store that value. Then we'll have to compute f of z is equal to p. Store that value. Once we know those values, we can say, oh, our gradient is just f prime of z times f prime of y times f prime of x. There's a forward step and a backward step. Forward propagation, backward propagation. Forward propagation to see what the value comes out of the neural network, and back propagation to get the gradient. Okay. So forward propagation evaluates the neural net and back propagation evaluates the gradient. Okay. Now, any questions so far? Okay. All right. So this looks simple enough for what's of an example with no real network connections beyond just one node to the next, right? Let's say we had, for instance, an activation function which we would never consider. So you have x and then the cosine. Then it becomes y. Then we have another function, it's our cosine. And the z, it's our cosine. And it becomes our output p. Let's compute comput, okay? P where x equals pi. That's easy. I think so. All right. So if x equals pi, cosine of pi minus 1, right? Unit circle, okay? But we'll remember that y is equal to minus 1. Okay? All right. What's the cosine of minus 1? Oh my goodness, this is getting scary first. Cosine of minus 1. Oh no. What have I done? I don't know the cosine of minus 1. Anyone got a calculator? It's okay. We'll write it. If anyone puts out a calculator, we'll put it down here. Okay, I'm trusting you. You got what you got? Radians would be lovely. .54. All right. Marco has volunteered for a job he doesn't understand. He's volunteered for just now. Thank you. So 0.54, right? Computed that, right? And finally, and we would store that to a much higher precision than 0.54. All right. Now what's the cosine of 0.54? 0.86. Okay? There we go. That's P. That was the forward prop. Right? Now, let's compute, let's do purple. Compute partial P partial x where x is equal to pi. We know that's going to be, via our chain rule, partial P partial z where x was equal to pi times partial z partial y where x was equal to pi and partial y partial x where x is equal to pi. And when x is equal to pi, I should say this is where z, sorry, where z was equal to 0.54. So we'll say z is equal to 0.54. And this is where y was equal to -1. And this is where x equals to pi. And each of these are functions, f prime, which is going to be which is the derivative of cosine, which we all know is minus sine. So f of x minus sine of x. All right, Marco, you're up. Can we do minus sine of 0.54? Radians, please. Minus 0.514 times. Now I need minus sine of -1. (0.84), stop there, and multiplied by minus sine of pi, which I guess is 0. 0, I guess. Hope I did that right. Yeah. All that effort. 0. All right. But you get the process? We went forward to evaluate, hey, what does the neural network say? This input, what's the output? Now let's take the derivative backward, right? And we didn't have to do any complicated derivatives. We only had the smaller derivatives. Correct. Question. Negative sine of x. Sorry, could you, where am I looking at here? Oh, sorry. Oh, you're asking what my terrible handwriting is. You could have just said that. No, I'm just kidding. So that's an x. I tried to fit in an x. I was my long-suffering class with my handwriting here. F prime of x. Sorry. I don't know how that wasn't obvious. No, I'm just kidding. Thank you very much, Christian. All right. Okay. Look at that process. Easy for that. Yes, question. Yeah. Yeah. Right. This is what Marcos with so 0.514 is the minus sine of 0.5 whatever, according to Marco. If it's not, it's his fault. So this is, maybe let's write this in more this concretely. So this is going to be the minus sine of z, which is 0.54. Yeah, kind of like a back propagation, if you will. Okay, all right. So, and similarly here, it's going to be minus sine of, so it was y of minus 1. Was that it? Sorry, here. Yep. Minus 1. Minus 1 times minus sine of pi. Yes? Sine squared? I don't have a cosine squared. Sorry. Oh, when you have cosine times cosine, no, it's not a. Oh, I guess you could call it a cosine squared. So I guess it's like a cosine. Yeah, it would be cosine cubed. Like this whole thing would be like cosine cubed together, right? Yeah, is that how it? Wait, no, not at all. Wait, is it? I'm not a trig guy. What? It's composed. Sorry. Thank you. I'm confusing myself. I blame me. Okay. No, cosine squared is cosine times cosine, not cosine of cosine. If so, you have a much easier time. Sorry, you have to repeat that. Yeah. Yeah, just, yeah, the activation of the y, yes. So it would be cosine of x. That's what y would be equal to. Z would be cosine of x. Okay, these are composed functions. They're compositional is the phrase we'd use for it. It would just be of this function, right? So we don't have to do the derivative of the big component. You're already using the backpropagation algorithm to handle the chain rule for you, right? That's the problem when you have functions within functions, is the chain rule, okay? And this one might not look too complicated, I don't know. You know, it depends on what you think, right? But imagine what it's going to look like when our network starts to look like this, right? We're going to have, we still want the derivative of that, but there's lots more inputs, lots more activated functions going into other activated functions and sums of them, right? But conveniently, people have extrapolated the patterns of what we just did here with this simple one node per layer network and did it for a larger, fully connected network for us, okay? All right. This is in chapter 6 of Goodfellow et al. Okay. Et al. Okay. So in Goodfellow, they use this notation, all right? Where you have what's called the network depth L, okay? And then you have W, which you recognize as your matrix of weights, like we covered on Thursday, right? But of course, we had multiple matrices of weights, right? Every layer had a matrix of weights because you have, every layer has an input and an output. So you have certain number of columns of inputs, sorry, rows of inputs, and a certain number of columns of outputs. So each layer is going to have a matrix, one, then the other, then the other. So they notate that as Wi, where I goes from 1 to L, which is the number of layers in the network, okay? So in the weighting matrices. The weight matrices. And they specifically call out biases as its own parameter to optimize separately, okay? So each layer has a bias from 1 through L. I did a little extra little doohickey there. Goodbye, doohickey. All right, my cousin's name. Those are our bias parameters. Okay. Okay. And you have X, which is a vector of inputs to the process, and Y, which is the target output. Right? Okay. We also have something called where J is equal to L of Y hat and Y, where that is your loss function comparing to your data. And J, generally speaking, people think of as the loss itself that comes out. It's like the cost or the loss. All right. in optimal control, we would see J as the cost function a lot of times in control optimality. So, all right. So we define these things where you have a, so let's draw this out. What does that look like? Okay. So if you have some inputs x, here I'm drawing inside the circles, I'm drawing the functions. All right. It goes into some function. And you have some other layer. These all technically have little arrows on them, but I'm not going to draw all of them. Actually, I am. It's already done. Goes into some other function. Right now, we'll assume we're all the same functions, but you could theoretically change the type of function from layer to layer. Nothing stopping you from that. And let's just go to some output layer with some function. Everything cool? Sorry, someone's having more fun than me. All right, you have some output y, which we will then evaluate with some function j. Now, this is the end of the network, technically. So technically speaking, we would say this has 3 layers. So that would mean that L equals 3. Okay. For each of them, we'd have maybe we'd have weighting matrices for each. 1, 2, 3. Definitely multi-layer, even though it doesn't have multiple hidden layers. Okay. All right. So Goodfellow and many other people have laid out a very clear algorithm for first forward propagation. We first have to propagate forward, store all those values in the middle, which we will then use when we propagate backward to get our gradient. Okay? So algorithm for forward propagation. I'm just going to put in parentheses, no regularization. We're not talking about regularization yet, just to keep it simple, okay? But it's an entire chapter of this textbook is regularization, all right? It's important, the regularization, but we're going to get the concept across without it today. Forward propagation, all right? So we're going to create some vector h, 0, meaning it's our 0th one, okay? And it's equal to x. And what these h's are going to be, they're going to be our intermediate vectors coming out of each of these nodes. So the values that come out of here, before they are multiplied by all of our weights, those are going to be h's. So this would be h1 would be what comes out of here. h2 is what's going to be coming out of here. Okay, we're doing red, coming up. And to be clear, that's not an exponent. You understand that that parenthesis is saying this is number 2. Okay? What's coming out of here is going to be h3, right? Which will ultimately be the output y that we want, that we will send into our cost function. And this technically is our loss function right here. No. Yeah. So we first initialize our first sort of set of, this is a vector. We store it. Okay. And we do what kids call a for loop. Hear it all over TikTok. Let's see. For loop for k. And 1 all the way up to L, do, so it's just continuing on the loop. This is what we call, by the way, we never talked about this. This is what we call pseudocode. Okay. Meaning it's not written in the literal code of a computer language. It's pseudocode. It's like the workflow. It's the process, right? Right? Yeah. Then we will compute the activation that goes into each of our layers is equal to BK, which is our bias, that's what we're adding, plus WK, which is our weighting matrix for that particular layer, times H of K minus 1. What's that doing? That's doing the fancy matrix multiplication, right? It's just a way of summing a whole bunch of values multiplied by other values. That's what's happening with this step. Okay? Then we then have to activate with our activation functions f by saying, hey, h of k, what comes out of that activation function, well, is the activation function times a of k. So what that a is doing, and I'll zoom out a touch, all it's doing is it's taking the output of the previous layer and multiplying it by all the weights, and then adding them as they go into each of these nodes. That's all it's doing. Then once it goes in, it comes out as h after it's gone through the activation function. Okay. Then you end the for loop. Meaning you loop and repeat that for each of the layers. Say, what's my inputs? Multiply it by the weights with this matrix math. Apply the function to all the elements in that vector, and then out comes the new input to the next layer. It just repeats, 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 repeats until you're out of layers. Then once you're out of layers, you say your prediction is equal to the h of your last layer, the output of the last layer. That's your prediction, y hat. So your cost is then going to be, or your loss is going to be equal to your loss function of your prediction, what comes out of your network, and your data. Done. Hey, all those fancy neural nets, the ones that do all kinds of fancy, they get more fancy than this sometimes, a lot of the time, but that's it. That's basically what we did in class as well on Thursday. It's just we didn't write this loop. We just manually said, oh, add all these together. Then we copied and pasted and said, here's a new weighting matrix. Add these together. Add these together. This is just it in a loop. Now I'm going to put it in a different color here. Here's the regularization term. Just a different color here. We were not ready to talk about yet. Okay, that's where it comes in. That's going to be the only difference for this part of the algorithm with regularization, but more on that later. That makes sense? Yes. Oh, the bias. So the bias is a vector for is a single parameter for each layer. So the bias is going to be a scalar value. Sorry. Oh, not scalar value. It's going to be one value per every input into a layer, right? So if the input of the matrix, if this was your weighting matrix here, okay, your bias would be same number of rows, just one column, okay? And that just gets added in. So that way it gets added to each of the rows that come out of this matrix multiplication. The way we handled it in class last time is we just added an extra input, which had the number 1, which was then multiplied by a weighting factor that we chose. That's what we did on class on Thursday. It's mathematically the same thing, but this specifically calls it out as a bias. So it's just a constant that can be optimized. We need to know what that is. We need to know you still have to know the gradient with respect to that bias, because we are also going to be changing that bias. Any other questions? Okay. All right. That's forward propagation. Now back propagation. Okay. All right. All right. So now we have to do back propagation. Keeping in mind that during the forward propagation step, we were computing and saving up these values of hk. They're in memory somewhere. So if we want to know what where k is equal to 2, that's stored as a vector in our memory. So we can go back to that once we do back propagation. Already stored as a number. Okay? Because that'll be referenced as part of the back computation step. Okay? All right. All right? So what we need to then, so we start off by saying that our gradient g, that's our gradient, we're going to initialize it, starting with the very last gradient that's in our network, in our whole process, right? Which is actually the gradient of the loss function. So I'm going to go up, sorry, I'm going to scroll it up again. The last thing we got out of this was the loss. So if we're back propagating the gradient, the first function we got to differentiate is that loss function. Okay? Now we did that in class for the mean squared error. It's just a square of a value, so we just becomes 2 times that, right? So it actually wasn't too complicated for a single data point. But we assign this whole little this little arrow here. That just means assign. Okay? What we want is the gradient, that's what the upside down triangle is, of our prediction, with respect to our prediction y, that's beneath, it's sort of a subscript, just to I'll make that a little more clear. Subscript there of j. Okay? So just as an example, I'm going to put this off to the side, that if our mean squared error, let's just say for just one data point, is going to be the square of the error, which is going to be y prediction minus y squared. This is a data point, it's some constant. This is the value of y hat that we have stored. Okay? Then the gradient of y hat for this example, really easy. It's just 2 times y hat minus y. Don't be scared by the notation. All right? Another way that people write this is because you have the actual function written in the loss function. They will say the gradient with respect to y hat of the loss function, which includes our prediction and our data point y. That's step 1. We initialize it. Right? Okay. Now we do a for loop. Again, we're looping. For k is starting from the last layer, back propagating, to the one before it, all the way to the very first one. Going back in our for loop, then we do this process. Okay? Keeping in mind, we have stored all of those values from the forward propagation. We say that the gradient is now equal to the gradient of the a of k, with respect to the a of k, of our cost. Now, what is that written a little bit more succinctly in actual terms of math we can do? Okay, it's going to be g leave a little space here. I'm going to put a dot here. Leave a little space though of f prime of a of k. Keeping in mind a was stored as a vector for each of the layers. The only tricky part is that this, given that the gradient is a vector and this is a vector, how do you multiply these things together? Well, we use a special kind of product which sounds really complicated, but is in no way actually complicated. It's a little bullseye. Okay? Okay? All it is each element multiplied by its pair. So if you have two vectors of the same size, the first one times the other first one. Second one times the second one. Third times the third one. Sort of, imagine the intuitive, so it's what this one is called. It's the Hadamard product. All it is that if you have some, what do we call it? Let's say we have a vector C, which has C1, C2, C3, and a vector D that has D1, D2, and D3. Then C, Hadamard product of D is just C1 times D1, C2 times D2, C3 times D3. Fancy name for a simple concept, right? That makes sense? Okay. They just want you to do an element-wise multiplication. For those who are MATLAB junkies, what command would that be? The period, yeah, the period multiply, dot multiply, right? Oh, not dot multiplication, period multiplication. Thank you, yeah. You were right, I was wrong. So. All right. So that's just the Hadamard product. So it means you started with this gradient, and now your new gradient is equal to your previous gradient multiplied by f prime times a of k. F prime, that's the derivative of that function, right? Now, typically, so whatever that activation function is, which is if it's cosine, which it's not, okay, could be the tan h. So the derivative of tan h is secant squared h. The derivative of tan h is the secant h squared of x. You can look it up in a table, okay? But it's just whatever the derivative of that function is. That's not too hard, right? And you apply it to every element in that layer, in that vector, sorry. Okay? Right? Now, you could do a regularization step. We're going to skip that from now. But then you want to continue the step back, because what you want to get is the derivative, so the gradient. Second, here we go. All right, got it. So now we need the gradient of, with respect to your biases. Because as Nate said, it's like, hey, what are the biases? There are things we have to optimize. Well, we have to optimize it. We need the gradient to optimize it. So here, in order to get the gradient with respect to the B of our cost, well, it's just equal to G. I believe, yes. And of our weights, and this should be B with a little k in the superscript to indicate it's the biases on that one particular layer. Here's the weights on that one particular layer. That's a capital W, just subscripted. How easy is that to follow? Not at all. So is equal to G H of the k minus 1th layer transpose. Okay. And then we assign the gradient again. We update it as being the gradient with respect to H of the k minus 1th layer. J is equal to W K transpose times G. Then we end the for loop. At the end of this G will have the gradient. Okay? All right. Now there are regularization terms as well. I'll add those in just for completion's sake. We're going to say plus lambda gradient of b k of some capital omega of theta. And here is plus, oh my goodness, I left no space for me. Plus lambda gradient of w kth layer times capital omega theta. I'm keeping it in different colors so you don't confuse it. What we're going to be coding up on Thursday. Okay? This is the systematized linear algebra version of what we were doing intuitively with a forward step and a backward step, with a forward propagation and a backward propagation. Okay? So you can notice, so any questions? I know it's a little complicated. Yes, Angela? Yeah.
Not doing. Why are you?
Let's see, W of K is equal to J of K, W K, gradient, next lower level activations. All right. Gradient with respect to H of K minus 1. It's a good question. I'm losing track of myself here. Yeah. Oh, well, let's see. Oh, well, because you need to, well, here's the thing. This gets propagated backwards because we'll need this on the previous layer, right? But at the current layer, we still need to know what the gradient is on the current layer for all those values. So they get stored because when we have to do gradient descent, we have to know what the gradient is of, I'm going to scroll up, of with respect to those weights and biases and those weights and biases. So it's storing them all. Hence why we have the little sorry, use the technical terms. Yes. For gradient descent.
Okay.
Right. Because backpropagation is just for the gradients. Right? Question. Yes. Okay. Yes. Specifically, that is a gradient is a vector, but yes. Yes. Correct. All right. Question. No, not for coding. No, it's just to really indicate that this is an assignment, right? I'll be honest, I don't know. Someone in computer science is going to come for me, but I don't know. I don't know why they use one versus the other. Call me crazy. Maybe it's just the mathematicians. If you say x equals x plus 1, that might make them mad as mathematicians. I don't know. Happy to learn though. Right. That's backpropagation. I mean, it looks a little complicated, and you'll notice there's a lot of matrix multiplications going on. A lot of multiplications of vectors times other vectors going on, right? So now if you were sitting down by hand doing those matrix multiplications, you would get carpal tunnel really quick, right? Okay, right? So now, of course, we use computers for it, obviously, but not just any kind of computer. So you can, of course, code up matrix multiplications on your programming language, which runs on your CPU. What's CPU stand for? Anybody? Central processing unit, right? One big centralized processor. And those go super fast. They're incredibly powerful, right? And they can do anything. Like all the instructions that you can do on a CPU, they're super flexible. They can handle tasks coming in, switching out. You know, all of a sudden you have a new task coming in that can read. I don't know. I'm not a computer architecture guy, but they're incredibly flexible, right? But they're doing it sort of all on a mainstream. Like people, if you go buy a computer, you say, oh, I have an 8-core processor, right? That means you have 8 cores, each of which is going to be doing a different stream, but it's still like one stream of a set of instructions over and over and over again, okay? So if you're doing a matrix multiplication on a CPU, which you can do, of course, we do it all the time, right? It's going to be, x1 plus x2 times, it's doing all of these processes in a row, right? However, when matrices get really big, because these weighting matrices, they're going to get huge if you have billion parameters, right? Those calculations for training become really complicated. They take a long time. However, linear algebra comes to the rescue. There are all kinds of fancy ways to be smarter about multiplying matrices, taking advantage of a lot of zeros in your matrices. You can take entire courses in what's called computational linear algebra. And moreover, if you want to do really big matrix math operations, you don't use the CPU. Anyone know what you use? GPU. What's a GPU? Giant processing. No, it's graphics processing. I like so they are giant these days. So yeah, so they're called graphics processing units because they're really good at the kind of math that you need for graphics, which is a lot of matrix multiplications. If you're playing a video game, to bring back the theme of video games, okay? In order to know what pixel values on that screen, and you have all these objects in front of you, you're going to have to do matrix transformations on all these things. And basically, you would never use your CPU to figure out what pixels go on your screen. It would be way too slow. These GPUs are really good at doing simpler tasks, specialized tasks, things like matrix operation tasks, and dividing up upon many, many, many cores, not like the 1 through 8 you might have in your CPU. Hundreds, maybe thousands of cores. You seen those, anyone hear about data centers in AI? Yeah. What do you think that's filled with? Basically GPUs. Now they have turbocharged GPUs. They have so things called TPUs and AI processing units. But one of the major things that people figured out was that GPUs are excellent at doing these matrix computations, both for gradient descent, for backpropagation, all this stuff. Okay? So if you are trying to build a gaming PC and your graphics card is very expensive, it's in part because the demand due to AI. Also, at one point, it was like Bitcoin miners found a way to do this well, right? So much of the computing infrastructure for machine learning is built around the fact that these giant matrix operations are really hard to do. They're much more efficient to do on specialized hardware, like GPUs. In fact, earlier in this big machine learning boom, people said, yeah, GPUs, that's great, but they're built for, not even directly for what we need. What about specifically a chip that's good for these big matrix operations? Okay, people know what a vector is. It's a one-dimensional matrix. Anyone know, in a two-dimensional matrix, we call a matrix. Anyone know what a three-dimensional matrix is called? Tensor, yes. And technically, all those things, matrices, are a subset of tensors, okay? T-E-N-S-O-R. Tensor. So they created what are called a TPU, or a tensor processing unit. Right? So when you're dealing with giant networks with tons of data, you want to do it fast. So if you're wondering how this all ties into what is currently the most successful, the most successful sector of our economy right now, for better or worse, okay? So much of it is built around having these giant data centers filled with computers that are good at this math. All right? Not just this math, but math like this. All right. That makes sense? So yeah. Okay. Well, we went from linear regression to backpropagation pretty fast. So I recommend getting started on the homework. Again, due Friday of next week, 5 p.m. I think it might be a little challenging at times. You'll be doing gradient descent with more variables for your regressions. So get on that. And good luck. I'll just take questions. 1 second.